Lord. All right, so today we're talking about atomic theory, different models of the atom. If you don't have a periodic table handy, go ahead and pull one out. You're going to be referencing it today. If you don't have one with you, I've got some up here. They have my office hours on the back from fall 2015. So if you want to know what my office hours were 2 years ago, you can look at that. The periodic table is still the same. All right, let's review the particles of an atom. Atoms are composed of protons, neutrons, and electrons, right? Protons, neutrons, and electrons. Today we are only talking about neutral atoms. In other words, atoms that have no net charge, right? We're not talking about ions yet. These are all ions. They have a charge. We're not looking at them today. We're just looking at neutral atoms. Protons represented as a P with a little plus sign. Neutrons, a lowercase n with a 0. And electron, little e with a negative sign. I think this is probably a review for everyone in here. And just to give you an idea, which of the three is the smallest, proton, neutron, or electron? Does anyone remember? Which one's the smallest? Electron, and it's by a lot, right? Protons and neutrons are about the same size. I mean, if we round their masses to 2 sig figs, 3 sig figs even, it'd be the same number, right? 1.672, 1.674, or 0.675 if rounded to 4 sig figs, right? Same exponent versus mass of an electron, several orders of magnitude smaller, right? So protons and neutrons are significantly larger than electrons. All right, look at your periodic table. Everybody find the atomic number. The atomic number is the number on top. It is the whole number. Atomic number is always a whole number. Atomic number is never a decimal. Okay, atomic number is not a decimal. So that's how you can distinguish them, right? The number on the bottom is a decimal. The number on the top is not. That is the atomic number, and it is defined as the number of protons. All right, so every single atom of gold, for instance, is going to have 79 protons in its nucleus. Not 78, not 80, right? 79. Because if we change the number of protons, that's how we change the identity of an element. So if you add 1 proton to gold, you will get mercury. That's element number 80, right? If I gave you a bar of gold, you'd be like, woohoo! If I gave you the equivalent mass in mercury, you would not be very happy about that, right? Poisonous, absorbed in the skin, not something you want. That's the only difference between gold and mercury, 1 proton, okay? So you can think of the atomic number as like your social security number, right? That's what identifies you. If I put a different social security number on my tax return, I'm in big trouble, right? That's identity fraud because I have 1 social security number, not multiple ones. Or at least unless you're breaking the law, right? That's a significant problem. So this is like your social security number, right? You change it, you're changing your identity. Every atom of gold's got 79 protons. Mass number, on the other hand, that number can be changed. Okay, we'll talk about that today. Mass number is a decimal. Excuse me. This number on your periodic table is a decimal. And mass number is always larger than atomic number. You can think massive, right? The word massive, big. Right? So the mass number is larger than the atomic number. And mass number is protons plus number of neutrons. Okay, so atomic number is just protons. Mass number is protons and neutrons together. So that's the difference between mass number and atomic number. Number of protons versus number of protons and neutrons. You're going to have a whole number for the atomic number. You're not going to have a whole number for the mass number. Questions on these 2 definitions thus far? Probably review. All right, let's just compare them again, right? This is your identity. You change it, you get a new substance. And another thing to keep in mind, we're talking about neutral atoms today, which is why number of protons equals number of electrons. When we start talking about ions, that's not going to be the case. But today, we're talking about neutral atoms, so that means the number of positives and the number of negatives are equal to each other. Again, mass numbers, protons and neutrons together. We'll talk about why that's a decimal, not a whole number, in a couple minutes. So if I asked you, what element has 31 protons? Would you find the element number 31? Or would you find the element with a mass number of 31? Which number do we go with? Top number 31, right. So you just break out your periodic table or look over there on the wall, right? Excuse me, gallium. That's an old periodic table. Woo, way old. Okay, we're going to write nuclear symbols in this class. Excuse me. Getting over that cold still. If you do not know how to write a nuclear symbol, you're going to know today. This X stands for the symbol, whatever it is, NE, NA, BR, whatever. Right? That's just a symbol. The top number is the mass number. We round the mass number in our nuclear symbols to the nearest whole number. Okay? We round that to the nearest whole number. The atomic number requires no rounding because it's already a whole number. So it's always M over A. M over A. Ma. Right? M over A. This is called a nuclear symbol. All right, so let's do an example. There's the nuclear symbol. What element is this? Fluorine, right? That's fluorine. So the top number here, is that the mass number or the atomic number? That's the mass number, right? M over A. We round the mass number to the nearest whole number in these nuclear symbols. Here's the atomic number, right? Mass number and atomic number. What if I asked you how many neutrons are in fluorine? Could you do that? This is protons and neutrons. This is just protons. So look at this, nice and convenient. If I want to know number of neutrons, this is set up for me that all I have to do is subtract. Right? I don't have to worry about getting it backwards. If I just look at my nuclear symbol, set up for me, 19 minus 9 gives me my number of neutrons. Okay? Questions on nuclear symbols? All right. Nuclear symbols. Now remember, we round the nearest whole number for the mass number, okay? Now there's another type of notation, it's called hyphen notation. The way we write hyphen notation is you write the name of the element, then you put a dash, and then you put the mass number. Mass number, not the atomic number, mass number, okay? So if I said, take this nuclear symbol and write it as hyphen notation, you would write carbon-12, okay? Mass number. If I said take this nuclear symbol and write it in hyphen notation, you would write name dash mass number. Okay, the top number, not the bottom number. It's the mass number. We'll talk about why it's the mass number when we talk about isotopes in about 5 minutes. So, questions on nuclear symbols, questions on hyphen notation. Maybe you've done this in the past, maybe you haven't. But now it doesn't matter what you did in the past because everybody's the same. Okay, so like I said, mass over atomic number. Let's go through this one together. Let's pretend that I gave you this on an exam and I said, all right, fill in the rest. Could you do it? This should be an easy calculation to do, right? Let's just go through it together. So first one I want to talk about is number of protons. How do I get that? The bottom number, right? Now, this is a neutral atom, so protons and electrons are equal, right? And how did I know that it was nitrogen? Element number 7. Now, what if I didn't put this? What if I just put an X right here? Could you still know that it was nitrogen? Yeah. If I was being really mischievous, I could have put an X right there and just given you 14.7. You just look up element number 7. And like I just said, protons and electrons are equal in neutral atoms, so that's how we got that. How do I get neutrons? Right, we're just subtracting. It's set up for me to subtract. And then in hyphen notation, what would that be? Nitrogen 14 or nitrogen 7? Nitrogen 14, right? It's always the mass number, not the atomic number. Okay, we'll show you examples of this, why it's got to be mass number when we talk about isotopes coming up in a few minutes. But before we get to that, let's make sure everybody's good at this. So try these on your own. You can do it in your head, you can do it on paper. Take a minute and give these a try. Make sure that everyone is all on board with this. Okay, let's go through the answers. Check your work. Do we agree? Do we agree? Beryllium 454, beryllium 9, sodium 11, 12, 11, 23, 11, Na, sodium 23. We good? We good? Okay, let's talk about what an isotope is. Isotopes are atoms of the same element with different mass numbers. Different mass numbers, okay? So they have to be the same element. So for instance, if one's carbon and one's boron, those cannot be isotopes. It's not possible, okay? They have to be the same element. And I could be, you know, mischievous here and give you X's, and you should still be able to tell that they're isotopes. Which number is going to be the same in isotopes? The bottom number is always the same, right? Because that's the atomic number. That's the identity. So you can think of isotopes like gaining weight, right? If you lose 50 pounds, have you changed your social security number? No, you're still you, right? You are still you. Your identity has not changed. You've just gained or lost weight. Same thing here. So here are 3 isotopes of hydrogen. Hydrogen that you're most familiar with, 1, 1, look at your periodic table, right? The mass number of hydrogen on the periodic table is 1.008. That means that this is the most abundant isotope. We'll talk about where that comes from in just a minute. But that's 1 proton, 0 neutrons, right? 1 electron. Deuterium, this is an isotope of hydrogen. How do I know? It's got the same atomic number, and it's got a neutron now. That's why its mass number is 2. And then this is an isotope of hydrogen. It's called tritium, right? It's got 1 proton, 2 neutrons. That's what gives a different mass number, okay? The identity, though, is always hydrogen because the mass number can change. The atomic number determines the identity, okay? Does this make sense? So if you make H2O out of tritium versus H2O out of protium, right, that water is actually going to be heavier. It's going to have a greater mass because the mass number of tritium is higher than the mass number of protium. Now we're going to talk about why the mass number on the periodic table is not a whole number. Does anyone have any thoughts about why? It has to do with the fact that all 3 of these are going to have different masses, right? So let's go over a couple more examples of isotopes just to make sure that everybody's good on what an isotope is and why we use hyphen notation using the mass number. Okay, so consider this. These are both isotopes of uranium, right? This isotope, I know it's an isotope because they've got the same atomic number. What's different is the mass number, right? 143 neutrons versus 146. Notice the isotope is written using the mass number because if I use the atomic number, they'd both be called uranium-92. Would I ever be able to distinguish them? No. Okay? That's why we use the mass number, because the mass number distinguishes between isotopes. If you write uranium-92 for this one, and then you call this one uranium-92 as well, yes, they're both uranium, but they're isotopes of uranium. They're different. So make sure you understand that's why we use the mass number for the hyphen notation and not the atomic number, so we can distinguish between isotopes. Do we understand what isotopes are and how we can tell if it's an isotope or not, right? Mass number is different, atomic number is same. So just take a second, think about this. Let's pretend it's a multiple choice question on an exam. How are chlorine-37 and calcium-40 similar? Are they similar in the number of protons? Are they similar in the number of electrons? Are they similar in the number of neutrons? Or is there no similarity? I'll give you 15 seconds to think about this. Consult your periodic table. And then we'll go over the answer. So the easiest way to do this quickly is just to write some nuclear symbols. So let's do that. This is chlorine 37. So that means the mass number is 37 or the atomic number is 37? The mass number, right? So that's 37 on top. What goes on the bottom? 17. How did you get that? That's the atomic number. Okay, now let's do calcium 40. 40 goes on top or on bottom? On top. So 40 over calcium on the periodic table? 20, right. Okay, so let's go through our options. Do they have the same number of protons? No, 17 versus 20. Do they have the same number of electrons? No, 17 versus 20. Do they have the same number of neutrons? Yes. Number of neutrons here is 20, right? 37 minus 17. Number of neutrons here is 20. 40 minus 20. So the answer here is C. Does this make sense? Okay, now, anytime the mass number that I give you in a problem, if it doesn't match what the periodic table has, that should be a red flag to you that you're dealing with an isotope. But the calculations, in terms of number of protons, neutrons, and electrons, that's no different whether it's an isotope or not. Okay, so don't let that throw you off. Okay, chlorine 37 is an isotope, but we still calculate a number of neutrons the exact same way. Okay, that part's no different. So just to confirm that, here are two isotopes, an isotope of one and an isotope of another. Take a second and try these, just to make sure you're good at it. I'm going to pause the video real quick. So just hang tight for a second. Let's go. So let's go through these examples. Check your work. Do we agree for carbon 13? Do we agree for potassium 41? Any questions on where these numbers came from? Questions, questions, questions. All right, let's talk about why that mass number on the periodic table is a decimal. Here's the answer. Think about your grade in this class right now. If I told you log in and look at your grade, is it going to be a whole number with no decimal places? No, it's not, right? Your grade in this class is a weighted average. It's not an average where you just add them all up and divide by the total number, right? It's a weighted average. Exams count way more than homeworks do, right? That's the bigger contributor to your grade, bigger piece of the pie. The mass number on the periodic table is a weighted average as well. And some isotopes account for a bigger part of the pie than others, okay? So it's an average atomic mass that is weighted. And so let's pretend that there are only two isotopes of carbon. There are actually 4, but 2 of them are just such tiny slivers of the pie that I combined some of them together. So this is technically the contributions of carbon 13, carbon 14, and carbon 11. Okay? But their slices of the pie are so tiny, I just combined them together. So what you do is and I would have to give you this data, you take the mass of that isotope times its abundance as a percent, okay, that goes right here, plus mass of the isotope times its abundance right here. Now, is 98.93% the same thing as 98.93 the number? No, right? How do you convert a percent to a decimal? Right, you just move the decimal 2 to the left, right? 98%, when I convert it to a decimal, move the decimal 2 over, okay? Because 12 times 98 and 12 times 0.98 are not going to be the same answer, not even close, right? The answer you come up with should match the periodic table within like the thousandths place, okay? So make sure you convert percentages to decimals. So when you give this, you convert that 98.93% decimal. 12.011, hey, that matches the periodic table. Now again, if your answer differs at the thousandths place, that's just rounding, no big deal. We're not going to get obsessive if you come up with 12.010 here, okay? That's just rounding. If you come up with 14.011. That's a problem, right? That's bad math. So go back and check your work. Also keep in mind, I could give you the mass number. I could give you mass, isotope, and then mass, and then I want you to calculate this abundance, right? You could do that too. That's just basic algebra. Okay? But I would have to give you some data to go from. I'm not expecting you to know isotopic data for all the elements. That's just insane. So here's one for you to try concerning isotopes of oxygen. Oxygen's three isotopes are oxygen 18, which is 0.205%. There's its mass number. Oxygen 16, there's its abundance and its mass. Oxygen 17, there's its abundance and there's its mass. AMU, by the way, stands for atomic mass unit. So I want to know what's the mass number for oxygen. Calculate it. See if you're right. I'll give you a hint. You matched periodic table, you did it correctly. I won't pause the video this time. I'll just make you go faster this time. Yeah, where did you find them? Oh, we've been over there a long time then. Yes. Sorry to interrupt you. Take a couple more seconds, finish this one up. Yep. So I'll give you two hints here before we go over the answer. Number one, you should know that your answer should match the periodic table, right? So you can look at the periodic table. The mass on the periodic table is 15.9994, I think, right? So your answer should be pretty close to that. Another way you can check yourself, your answer should closely match the most abundant isotope, right? So this isotope accounts for 0.2%. So should my answer be close to 17.9? No. This isotope accounts for 0.038%. So should my answer be close to 16.9? No. My answer should be really close to the most abundant isotope, right? 99.7% of it has a mass of 15.9949. And again, this is why I use our grade as an analog to this too, because if those three exams that account for 45%, you get 3 A's on those, the probability of you getting an A in the class is pretty high, right? Because that's the biggest piece of the pie. So the answer that you arrive at should be closest to the most abundant isotope, which it is. And again, the unit AMU, 15.9994, which should match your periodic table. Now, some periodic tables vary in the number of decimal places that they give, right? The one that I gave you is our one that we're going off of. And if your answer varies in the thousandths place, that's just rounding. If you came up with 20, that's not rounding. That's something's wrong with your arithmetic. And if you come up with like 45,000, you probably forgot to move the decimal before you started working, right? Make sure that you move the decimal so that we convert a percent to a decimal. Questions on this one? All right, we're going to shift gears a little bit, and we're going to talk about models of the atom and how we developed atomic theory. If you think back to the beginning of the semester, I told you that science is a process and it's a continual process, right? We don't just say, all right, this is our theory about whatever. Now we're done, let's go study something else, right? That's not how it works. As we develop in our ability to perform better experiments, right, that sometimes makes us have to rethink our model. So these are the experiments that you're responsible for. These are not the only experiments on atomic theory. Just want to put that out there. These are just the ones that you're responsible for, okay? So the first experiment / model pair that we're going to talk about is the Thomson model. Maybe you've heard of this from physical science or physics, high school. Let's talk about it. It's called the cathode ray tube. And it discovered the electron, essentially. So what we have here is a particle of, it's a beam of particles, okay? And then we took, well, I didn't do it, I shouldn't say we. Thomson took a magnet and held it in the area and looked at what happened, right? So the ray bends in response to a magnetic field. What does that tell me? That tells me that the beam is composed of charged particles, right? Because if it responds to a positive or a negative field, that tells me that the particles themselves are also charged. Now when we look at the negative versus the positive, when you hold the positive end, it bends toward the positive. When you hold the negative, it bends away from it. So it's attracted to the positive and it's repelled by the negative. So what does that mean? The electrons are negative, right? Negative goes toward positive, negative goes away from negative. And then the other thing is, doesn't matter which cathode you were using, you get the same results. So these particles are universally present, right? It's not just this one sample. It's being discovered in lots of different types of samples. So the Thomson model of the atom, you are responsible for being able to sketch / identify this. Thomson's model states that the atom is positively charged. You can think of it as like a positive sphere with negatives just randomly distributed throughout it, okay? So think about it like a chocolate chip cookie, right? That's delicious. When I used to teach this, back before I got mean, I'm not nice anymore. But when I was back in my nice days, I used to give my students chocolate chip cookies. I don't anymore because I'm aware of allergies because of my own children's life-threatening allergies. So now we just imagine a chocolate chip cookie because I don't want someone having an anaphylactic episode during class. That would be bad. So we just imagine a chocolate chip cookie, right? Positive sphere with negatives randomly displaced throughout. And again, this is the Thomson model. So be able to sketch it, be able to explain what experiments led to it. If you can understand the cathode ray tube, you can understand the Thomson model. That's all I need you to do. Is there more to it than that? Yes. We're just getting the condensed version, okay? Questions on Thomson's model. Now, is this the currently accepted model of the atom? No. Okay, if it's not the current model, what's wrong about it? Well, there are lots of things wrong about it. The big problem with the Thomson model is it implies randomness and order at the same time. What do I mean by that? Let's think about it like a chocolate chip cookie. If I've got my big bowl of chocolate chip cookie dough, right, and I'm spooning it out and putting it on the tray, yes, each cookie is going to have random distribution of chips, right? But is every cookie going to be identical? No. Now for atoms, all atoms of the same element had better be identical. But you can't have random and identical at the same time, right? That's not possible. Another way of thinking about it is if you take a deck of cards and you just throw it up in the air, right? Is it going to land the same every time? No, of course not. So you cannot have the same in every single atom, but yet random in every single atom. Does that make sense? Order and random at the same time, those are mutually exclusive, right? You're either ordered or you're random. So if they're randomly distributed, then if it's the same way every time, then they're not randomly distributed. One or the other. That's one of the biggest problems with Thomson's model. It assumes something that you can't assume. Does this make sense? No. There are some mathematical problems with Thomson's model. We're not going to get into that. Let's talk about Rutherford's model. If you took high school chemistry, you probably studied Rutherford. I'm going to sketch, maybe. I'm going to sketch this so that we can just see it. So Rutherford was testing Thomson's model of the atom. And so the way it worked is there was a radiation source, and what it was doing, it was emitting alpha particles. An alpha particle is just a helium atom. Oops, 4, 2. Okay, so it's just a helium atom. So you have a radiation source that's spitting out alpha particles, okay, helium atoms. And then you've got a detector area. Now, if you look at the figure in your book, it's like a big arch, but I'm not going to draw the whole thing. And so you're detecting in this range. All right, and then we've got a sheet of gold here in the middle. Okay, so I just draw that by a line. But really what we want to be able, let's imagine we could see the atoms. Okay, if you could see the atom, and Thomson is right? Thomson says that it looks like this, random distribution, right? That's what Thomson's model says. So if I am shooting BBs or marbles or whatever you want to visualize, right? Some of them are going to just deflect, and some are going to go straight through, and some are going to deflect, right? You should have random deflection, and you should have random transmission, right? In other words, the amount of deflection should be equal to the amount of ones that go through, right? Random deflection, and also a lot of ones that go through. So I didn't really proportionately draw that. Right? You should have a whole bunch that go through, but you just also have a whole bunch that deflect. Right? Does that make sense? That's what you would expect. Now, what happened here? Well, I'll show you the deflection, and then you tell me what that means about the model. So what was observed is a whole bunch of deflection in certain areas, and not a whole lot being detected in a particular area. In other words, there are ones going through above here, and all these are all going through. All these are all going through. But then there's a whole lot of deflection coming from a central origin. What does that lead us to conclude about the atom? I heard someone say it, I thought. There's a nucleus, right? Because if there is a nucleus in the middle, that would cause a bunch of deflection, and then everything else would go straight through. Does that make sense? So if your model doesn't match reality, you got to fix your model, right? Your model's got some flaws. And so Rutherford's gold foil experiment demonstrated the existence of the nucleus. Okay, that's what the purpose of the gold foil experiment was, to demonstrate the existence of the nucleus. That's what we expect. That's what we observed. And so Rutherford concluded there's no random distribution. In fact, it's all, the majority of the mass is focused in the center, right? That's the discovery of the nucleus. So it's the majority of the mass, it's very dense, it's at the center of the atom. And just to give you a frame of reference, okay, I won't make you memorize this for an exam. Let's just look at it. The average atom has a radius of about 100 picometers, whereas the average nucleus is 0.005 picometers, right? 5 times 10 to the negative third, that's a radius of a nucleus. That's the atom as a whole. So the radius is significantly smaller than the atom as a whole, right? Very small, compact, very dense in the middle. Does this make sense? Do you understand how Rutherford's gold foil experiment worked. What we expected didn't match what we got. If our model doesn't match reality, and it's not a problem with our experiment, right? Because first thing you go, maybe I just messed up, right? You go back and you test, and you test, and you test, and you test. You go, no, this is definitely what it looks like. Well, then we have to rethink our model. So Rutherford's model, you're probably familiar with. Copyright CBS, don't want to violate copyright laws here, right? Okay, if you watch this show and you look at the little symbol that they have on it, that's the Rutherford model of the atom. Because you can't forget electrons, right? Rutherford didn't forget about electrons. He said, okay, we know electrons exist because of Thomson, and they're not just randomly distributed. The center is where all the mass is focused, and the electrons are just out here around in random paths, okay, just randomly. So that's the Rutherford model of the atom. If I asked you to sketch it, that's what I would expect you to draw. Okay, compact center, random pathways for all the electrons. So you can think back of the symbols that they use on that show. That's a show you watch. People always assume that I watch the show because I'm a chemist, but I actually don't. Sorry, CBS. I know. Although there are things from the show that I will pick on later in the semester. Because I have seen some episodes, and there's a lot of bad science. It's kind of funny, too. All right, now, is Rutherford's model the currently accepted model of the atom? No, it's not. So that meant that there must have been something wrong with it, right? If it's not the current model, something's wrong with it. Well, the big problem with Rutherford's model is it didn't take into consideration the relationship between matter and energy. Okay, if you go home tonight and you turn on your stove, and you turn it on high and you walk away, you come back, it's going to be orange red, right, depending on what setting you have it on. So matter is emitting energy, right? Matter is emitting energy here. Something's going on. And so Planck, which we'll deal with this calculation along about week 13, week 14. I just want to introduce it here. Okay, Planck's constant is this value right here. Okay, and what it is looking at here is the relationship between energy and frequency. Okay, so there is a relationship between frequency and energy, and this is called Planck's constant. We'll get into some calculations with Planck's constant later. But what the problem is, that's not being taken into consideration here, is around the early 1900s, science started understanding that energy is absorbed and released, okay? And it's not just absorbed randomly in random amounts, it's absorbed and released in specific little packets, which we call quanta, okay? So if those electrons in orbit around here, you should be able to observe that energy in packets. You should be able to see that there's some sort of energy radiating from that motion in specific quanta. And Rutherford's model doesn't take energy into a factor at all. Completely silent on that issue. So we need to, again, say to ourselves, well, model doesn't match reality, so let's go back and work on our model. So Bohr's model is one I'm sure you're familiar with. It's very commonly taught as the currently accepted model of the atom, which is kind of bad. I mean, I understand teaching it to second graders this way because they're not ready for quantum mechanics yet, but we don't want to teach, this chemistry class as the current model. So Bohr made a lot of corrections to Rutherford's model, woohoo! But there are also lots of other problems that Bohr doesn't address. So the Bohr model says electrons are in specific paths around the nucleus. We call them orbitals, so they're not random paths. They are in specific paths. Planetary model, sometimes what it's called, right? Like the planets orbiting the sun. Even though we don't orbit the sun in a circle, we orbit it in an ellipse. Yeah, you get the idea. All right, so if I asked you to sketch the Bohr model, you would be sketching right? You would be sketching something like what you've seen before. Here's your nucleus, right? And then your electrons are in, right? We've seen that kind of model before. Now in the Bohr model, each orbit has energy associated with it. This one's low energy, this one's high energy. Bohr did get this right. Along about week 13, we're going to come back to atomic theory. We're going to do some Bohr model calculations. And one of the calculations that Bohr has right is that when you add energy to the electron, right, the electron jumps up in energy level, and then it's not going to stay there, right? Just like if I go eat a whole bunch of sugar, I'm bouncing off the walls. But I'm not going to stay that way forever. I'm going to come back down in energy. Same thing happens if I promote an electron up, it goes up to a higher energy level, and then it'll fall back down to the state it was originally. And when it does that, it releases energy in the form of light. And that's something that Bohr got right. Okay? If you are a student of physics and you've used, I guess you probably do this in Physics 1, I'm thinking, right? You've seen the Balmer series for electrons. Okay, that's all fine and dandy in Bohr's model. All right, but there are some other problems with Bohr. Another way to think about the energy levels in Bohr is like a ladder, right? High energy versus low energy. Falling off the top of the ladder, that's really bad. Falling off the bottom of the ladder, you just look silly, right? You're not going to break your leg falling off the bottom. Most people, at least. I might find a way to, but most people probably wouldn't. Whereas if you fall off the top, that's really bad. So Bohr's model had some fatal flaws as well, and the primary one is that it works for for atoms with one electron, i.e. hydrogen, right? If you've got one electron, this model works great, but that only accounts for one element, right? When you start adding that second electron, now there are all kinds of interactions between those two electrons that are not factored into Bohr's model. And I'm going to compact a whole lot of physics history right here in a few sentences, because we're going to come back and unpack this more in about week 13, week 14, but I just want to kind of lay the foundation now. Essentially, classical mechanics, right, the physics of when I throw a baseball, for instance, it just doesn't support the idea of electrons being in these fixed pathways. It doesn't work. One of the reasons why was contributed by de Broglie. And so his conclusion was that light acts like a particle and it acts like a wave. Right? So things behave as if they are particulate and as if they have wave properties, the dual nature. And so objects like us, we're so massive that our wave properties aren't observable. Right? I mean, you technically have a wavelength, and we have frequency, yes, but you're not an electron. So your mass is large and overrides the effect of your wave properties. But an electron, now that's a different story. Okay? They behave differently because their mass is so small. So we're condensing a whole lot of physics and a whole lot of science history into two sentences here. The bottom line being classical mechanics, which is the mechanics of, running down the street or catching a baseball. That's classical mechanics. It doesn't work. We need to have physics that works on the quantum level, the atomic level. And so the modern, currently accepted model of the atom is called the quantum mechanical model. We get back to this in week 13/week 14, and we spend an entire week talking about it. Okay, so I'm not going to get into the nitty-gritty details of the quantum model now, because we spend a whole week on it towards the end of the semester. I just want to lay the foundation now. And I just want to also throw out there, we're not going to look at any one person. We're going to look at quantum mechanics as a whole. But I do want you to know it's the currently accepted model of the atom. It's a mathematically based model. And we're going to talk a lot more about this in a few weeks. So here's a summary of today. All right. Thomson Model. What developed it? The cathode ray tube experiment. What's the problem with it? You can't have disordered order. It doesn't work. Rutherford Model, developed by the gold-foiled experiment. But there's no relationship between mass and energy. Bohr's model, we didn't We didn't talk about any specific experiments today. We'll talk about those in week 14. But the big problem there is it only works for one electron system. And the quantum model is the current model. And I also want to show you this. This is a link to Purdue Chemistry Department. Has a really great little website. If like the history of science is something that you find fascinating, you know, you want to read more on, you can go to this website. And it's divided by scientists and experiments. So you can read on specific experiments on, you know, electricity or electromagnetic radiation. Or you could go look up things about specific scientists. So again, if you're really interested in the history of science and how science has changed over time, you want to check this out. So that's where we're going to stop for today. And I will see you on Wednesday.